Hello. So we're moving on to chapter 2 in the Solomon's book. So this one we're talking about functional groups. So those are the parts of the molecule where there's actual reactivity, and that's what gives it most of its properties. So the most basic functional group is really the hydrocarbons. Those are the most basic organic compounds. Those are ones that only contain carbon and hydrogen. And so the simplest ones, they only contain carbon-carbon single bonds. So in this case, these two rings, and so this is, they are called alkanes. So, and we'll talk about how to name these in coming chapters. If there's a carbon-carbon double bond in there, they're called an alkene, and a triple bond, it's an alkyne. So this originally was actually it was Ionic, but later they changed it to Ionic for pronunciation, I believe, or to really mess with you guys. But this was actually, if you notice the alphabetical nature of these, the A, E, and originally I, that was actually by design. One of the few things that was actually makes a lot of sense. So like alpha beta pinene, so it's an alkene because it's got the double bond here. There's the alkenes here, so here there's a carbon-carbon. So if you have this like this, CH3, don't forget that there's a carbon here, 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 and then obviously the CH3. So there's ones there. For this one, that group there, right, there's a carbon. So for this part of the molecule here, there's carbon, carbon, carbon. There's a carbon here. There's a carbon there. But notice how with this carbon, there's only 3 bonds shown. It's a skeletal structure, right? So there means that there's a hydrogen there. So that there is still a hydrogen hanging off of there. So ethynyl estradiols. So benzenes, aromatics, these have benzenes in them. So this is a benzene right here. So it's a 6-membered ring with alternating double and single bonds. So double, single, all going all around. So there's actually a benzene here. There's a benzene here. This is not a benzene, nor is this one. This isn't a 6-membered ring. It has to have the three bonds. It has to be a 6-membered ring in order to be a benzene. There's other times when you can have aromatics, and we'll talk about those later. So let me turn the brightness down a bit. Okay. So wrong way. So again, the benzenes, they need to be the aromatics. This double single going all around. So this is the kekule. This is the that's the skeletal structure of them. But again, they only contain carbon and hydrogen. So they can, because of the resonance structure, you can move these around. And actually the resonance hybrid actually has them smeared around here. And the amazing thing about benzene is the fact that each one of these carbons is sp2, because don't forget there's a hydrogen hanging off of here, so there's 3 groups, so it's sp2. So that means that they all have a free p orbital, and they're all aligned like this, and stuff like that. And so what can happen is the electrons, all of these p orbitals are touching each other, and so if you look like this, what actually happens is they actually smear around here. So the best way to sort of think about this is to take two donuts, stuff like that. The 2 donuts with like a burger inside of it. That's one of the things I've seen here lately. A cheeseburger with, instead of a bun, they have donuts, like Krispy Kremes or something like that. So the Krispy Kreme, and where the actual atoms are, that would be the burger. So that's, if you want to think of a visual, that's the best I've been able to come up with. So polar covalent bonds, we talked about ionic bonds and covalent bonds last time, but but polar covalent is sort of the mix of the two. It's still a covalent bond, so they're still sharing electrons, but the sharing is unequal. Okay, and so because of electronegativity differences, so fluorine's a little more electronegative than hydrogen, and so the electrons are going to spend more of their time down by fluorine, and so that makes this side a partial negative and a partial positive. And so we use a lowercase delta with a plus and minus with that. And so I don't really consider CH bonds to be particularly polar covalent, but like CO bonds, stuff like that. So it doesn't matter if it's a double or a single triple bond. We're just looking at electronegativity differences here. and so oxygen's more electronegative than carbon. So there's on this carbon and this carbon, there's going to be a lot more electron density than in the middle. How about that? And so when you have this, one of the ways that you can do this, you can do the symbols. You can also do an arrow that goes from the plus to the minus. And the way that you remember which side goes where is, notice how this looks. This has a this kind of looks like a plus sign. So so the cross hash of the arrow goes on the plus side, and you're pointing towards the negative. Stuff like that. And so you can kind of, if you were to point all of these in here, what you can get is what's called a dipole moment. And so if you have these polar covalent bonds, they can sort of, if you add them up, what can happen is one side of the molecule may have more more electrons than the other, and so it sort of gets this what's called a dipole moment. You can sometimes see this as a little micro sign, stuff like that. So, but really, what you're doing is you're averaging out all those little arrows and stuff like that. And so now, don't think of dipole moment and polar character. They're two different things. Okay, so methyl chloride here, that has a much higher, that actually has a very high dipole moment along with methanol. But this is not particularly soluble in water, but this is infinitely soluble. So about that. So, and also don't forget, electronegativity is about individual bonds. The dipole moment is the sort of, if you add them all up. Okay, so about that. So symmetrical molecules don't have dipoles, right? So if you average these up, right here, you have equal and opposite. They're pulling at the same rate. There's actually no dipole, even though you have polar covalent bonds. The overall dipole is 0. Here you've got you only have the one polar covalent bond, so it's all going to go that way. Okay, lone pairs give that negative character to them, right? So that they act, because they're electrons, right? They're negatively charged, so they're going to act like partial negatives. Okay, so here's some dipole moments. Notice that if you're, even for things that are very electronegative, like chlorine, you've got it's symmetrical, right? So that the pole is equal and opposite. So with that, so the dipole is 0. These two, because the molecules are symmetrical, they're 0. CH4. Carbon tetrachloride, but if you get slightly off, right, so with that, so you will get the you'll have a dipole moment. Okay, so for something like carbon tetrachloride, you've got carbon in the middle and chlorines on the outside. So even though you have polar covalent bonds, they're pulling equal and opposites, just like carbon dioxide, equal and opposite, and so the overall molecule is not going to have a dipole. Okay, so cis and trans isomers will also have a dipole. You say cis will. Good, right? Because you've got two polar covalent bonds are both pointed the same way. In this case, they're down. So like that, so the overall molecule is going to have a dipole moment, halfway in between. So it's going to go this way, between them. But in the trans version of this, so they're equal and opposite. The polar covalent bonds, they're pointing in opposite directions equally, and so the trans version has no dipole. So this has a dipole. This one does not. Okay. So if I ask you about say Cl, H, right? So with that, so you're going to have a polar covalent bond going this way, one going this way, and then the overall would be this way, overall. Okay. So with that, and so if we had BF3. Okay, we're going to have 3 dipoles, right? Because fluorine's a lot more electronegative than boron, so they're going to point this way. But since they're all equal and opposite, there's no dipole. Okay, there you go. Okay, so for alkyl groups, these are carbon groups that are away from the main chain, stuff like that. And so we'll talk about more. I just want you to recognize them, that that you can have groups coming off. So that, so one carbon group is called methyl, 2 carbons ethyl, 3 propyl, 4 butyl. We'll talk about this more, about how to do the naming. If you want to memorize anything off of this chart, it's these abbreviations. Me is methyl, ET is ethyl, PR is propyl, BU is butyl. Sometimes people write that if they just need for simplicity's sake. Stuff like that. But we'll talk more about the naming of these. But just realize that you could have the main bulk of the molecule, and then you have things coming off, branches coming off, and sometimes these are just regular alkanes, so we call them alkyl groups. And notice how one of the reasons why we call it, it's an alkane, right? Alkane. What we're going to do is when we denote a side chain, right, it's going to have that ly suffix, right, so that we call it an alkyl, right? Alkane to alkyl group. So that'll come up over and over again. Okay, so sometimes you'll see this designated as an R if it just means any of them. Any sort of alkyl group, it doesn't matter if it's methyl, ethyl, propyl, isopropyl, hexyl, or whatever you want, cyclohexyl, whatever. Stuff like that. If it can be anyone, basically that end of the molecule does not matter. It can be anything you want. Stuff like that. So sometimes that's designated as an R. I usually don't write that, but sometimes I will. I mean, it does pop up from time to time. Now, if you have a benzene that comes in as a side chain, so as a branch, stuff like that. Sometimes it's written like this. Sometimes it's written as the resonance hybrid, where you just have a circle. This is one of the few times where you can write this as a circle, as the resonance hybrid. If you don't need to react on the individual bonds, or it doesn't matter. So by that you can sometimes put this C6H5, sometimes with a pH. So by that, sometimes it's given this symbol, the circle with the cross. I can't remember what this Greek letter is. I think it's not psi. Anyway, not that much. Sometimes it's R if you have things coming off of it, off the benzene. Sometimes it's written as AR. Something like that. So these are all what are called phenyl groups. They always represent a phenyl group, but it's just a benzene, just a plain benzene. You can also get it as a benzyl group. This doesn't come up very often, but everyone's. If you between the main chain and the benzene, there is a CH2 in between there, linking it to the main chain. It's called a benzyl, and this is sort of a historical quirk. So if the phenyl should have probably been named benzyl because it makes more sense. But basically, what they did is in the Victorian London, when they were trying to have the gas lights, they had these residues that were left over. They were studying those, and they thought they had a benzene, so they called it benzyl. But in fact, they had the CH2, and nobody ever got around to correcting it. So it has to connect through CH2. So alkyl halides. This is just a regular carbon, regular carbon alkane, stuff like that. So with a halogen so this is fluorine, chlorine, bromine, iodine on that row of in the halides next to the noble gases, and you'll see this a lot where we have we talk about primary, secondary, tertiary carbons. What we're saying is this carbon here, how many other carbons are directly attached to it? Only one of this. It doesn't matter if it was, say, this, right? If you're going to have the Cl here, that would be a primary carbon because there's only one carbon directly attached to this other carbon. Okay, there's only one of them. Here, this is secondary because it has two carbons directly attached. This is tertiary because there's 1, 2, 3 carbons attached. You can't have quaternary carbons where there's 4 things attached, but you can't also have that be a halide because you need some place to put the halide. Stuff like that. And so we're going to talk, because this is going to be important as we go down there, because primary and tertiary carbons, and sometimes secondary, they can give slightly different results, or they have to react slightly differently for a variety of reasons. Okay, so again, so if you're the carbon you're interested in, if it only has 1 carbon attached to it, it's called primary. If it's 2, secondary, 3 carbons attached. Now, these things could have whatever they wanted to attached off of there. They could be just CH3 groups, that's fine, or they can have like 20 carbons long. They can have a benzene hanging off it. It doesn't matter. You just look at the individual, you look at the 4 individual atoms that are attached to that carbon, and if 3 of them are different carbons, then that's tertiary. You can also have the quaternary here. Okay. So alcohols, those are regular. Those are just OHs hanging next to just a regular alkane, stuff like that. However, if they are they're hanging directly off of a benzene, like this one. So that is, notice how that is a benzene. Oop, that right there is a benzene. Stuff like that. It looks very much. It looks like this benzene. If the OH is hanging directly off the benzene, then it is called a phenol. It has slightly different characteristics to it. That having that double bond right off of right next to that OH makes it a little bit different. So those are called phenol. But notice how this alcohol here, it just has regular alkanes next to it, so it's just considered a regular alcohol. So here, this is a phenol. That's an alcohol. This is what's actually called an enol, but we won't have to worry about that. Alcohol, again, enol. It's like that. So it's a mix of alcohols and phenols and other ones. Okay, so again, this is just like the alkyl halides, where that OH attached, the carbon where this is attached. If there's one carbon, so here, right, there's this carbon, there's only one other carbon attached to it, so it's primary. Again, this one, there's a carbon here, only one other carbon attached. Here, menthol, right, so that carbon only has 2 carbons attached, so this is secondary. Here in norethindrone, something like that. So it's a steroid, stuff like that. So it's an oral contraceptive. So this carbon here, it's a little hard to see, but there's 1, 2, 3 carbons attached to it. So to that carbon, the other 3 bonds are attached to different carbons. So that's tertiary carbon. It's a tertiary alcohol, let's say. Okay, ethers. So these are, instead of being a carbon with OH, it's a carbon, oxygen, another carbon. And so they have this general structure. So for that, so this is the simplest dimethyl ether. So there's a carbon, O carbon, carbon, O carbon. So this is, you can even have them in a ring. So like this, so carbon, oxygen, carbon, no problem. So this actually has a special name called an epoxide, but we'll talk about that later. So about that, so tetrahydrofuran or THF. This is a common solvent. It's a nice solvent. So you can have amines. So if you have nitrogen groups, so with that, so these are just these are just regular nitrogens. We'll talk about amines in a minute. There's a special case with nitrogens, actually 2. So with that, but what you can do here is you can have these, different things hanging off it. They usually smell pretty bad. Thus the name putrescine. So this is a diamine. So there's 2 of them. So with that, so these are very length carbon chains, and they all just they smell like rotting meat, stuff like that. So they all have real fun names like this: cadaverine, putrescine, all sorts of fun names. This is the general structure for an amphetamine. The methamphetamine has a CH3 group, a methyl group hanging off of one CH3 group hanging off the nitrogen. Again, the amine classification. Now here it's how many carbon groups are hanging, or other groups, usually it's carbon though, are hanging off of the nitrogen. So you can have 1, 2, or 3. So here these are both primary, right? Because they only have 1 carbon hanging off, 1 carbon hanging off. This is a tertiary, so it's 1, 2, 3. And this is technically, I guess you could technically call this to be a secondary, right? Because there's 1, 2. Secondary carbon, because there's only 2 carbons on there, but this is a tertiary, so 1, 2, 3. Aldehydes and ketones, so you'll hear me talk about this a lot. This is what's called a carbonyl group. It's a C double bond O. This becomes incredibly important for doing chemistry because it has a really nice polar covalent bond with these double bonds. One of them, they're always going to have a carbon on one side. Well, pretty much always. But if there's a hydrogen on the other, so our carbon on one side, hydrogen on the other, it's called an aldehyde. For a ketone, you have carbons on either side. Now this one is usually abbreviated COH. So but that, CHO. So if you have an aldehyde, so if you say R, whatever it is, so if you had C, CH2, CHO, we're going to interpret that as CH2 aldehyde. Now the reason why we do HO is because if a chemist saw COH, what they might be thinking is that's an alcohol. Oops, I can't see that. I hope if you can see it. So if you had CH2 CHO, you know that this is the aldehyde group. Not to be confused with COH. You might think that this is just like a regular alcohol group, and then I don't know what happened to the other hydrogens, stuff like that. So you just have to be careful. Okay, so that's how they abbreviate it. I try not to do the abbreviations, but sometimes they pop up, so just be aware. Aldehydes and ketones, these are typically things that have pretty good scents to them. So trans-cinnamaldehyde is the active ingredients in cinnamon. Carvone is in spearmint. But that so there's also another version of this that's actually has a savor. It tastes like caraway. Stuff like that. But they have this ketone here, right? So C double bond O with carbons on either side. Acetone. This is what's usually used in nail polish remover. Methyl ketone. So right there, ethyl methyl ketone. But this is sometimes abbreviated MEK. Stuff like that. So benzaldehyde. This is typically used in almond or cherry flavorings. Something like that. So acetaldehyde, formaldehyde. Actually, formaldehyde is one of the quirky ones where it actually has hydrogens on either side. Usually, it's just a carbon and a hydrogen. Formaldehyde is the exception. But this is a preservative. Stuff like that. So, yeah. Carboxylic acids. So this is one of those quirks where you have an OH, but right next to it, has to be right next to it, is a C double bond O. So if it's just a regular carbon, just like a CH2 group or something else, it's just an alcohol. But if it's a C double bond O, like this, it's a carboxylic acid. Okay, so this is formic acid, acetic acid, benzoic acid, right? All the OHs have a C double bond O next to them. Esters, instead of having the O, it's like a carboxylic acid, but instead of having the OH here, it's an O and then a carbon group, another carbon group here. And so these guys here, they usually smell really good. So pentyl butanoate, and this is in apricots and pears, stuff like that. So, and a lot of these fruit smells, they just vary the lengths of this carbon chain and that carbon chain, so like that. So a good trivia is about the banana. So artificial banana was developed in the 1940s, 1950s, stuff like that. So, but the problem was the banana that it was based off of in, I think, the 1960s, because bananas are all clones of themselves. There was a fungus that got in there and destroyed, and basically wiped out that version of the banana. And so another banana was introduced, which is the Cavendish right now. So, but that it didn't have nearly the flavor or the texture or anything like that, but it's still a banana. So people do like it. But the original banana, I can't remember what the strain was called, but it had this wonderful sort of banana taste from the banana flavoring. This very creamy texture was very good. Stuff like that. But they never got around to changing it to be like the new Cavendish, because the Cavendish doesn't taste as good. Stuff like that. So the reason why banana flavoring doesn't taste like bananas is because the banana has changed. Now the problem is the Cavendish is also, clone is also, all of them are clones, and so the problem is there is another fungus coming in there, so we could, what was it, and so they could be wiped out here in the next decade. But so there is efforts to do a GMO to be resistant to this, but because of the anti-GMO sentiments, they may not be introduced, and so in 10 years we may not have bananas anymore. So you have to be careful. But anyway, esters, they smell good. So it's now amides. So these are not to be confused with amines. Okay, so they still have the nitrogen here, but again, they're like carboxylic acids where they have the C double bond O right next to the nitrogen. Okay, so it has to be right next to it. So this is called an amide. So by that, these are a little bit different. We'll talk about the naming of what this means. It just means these groups are hanging off the nitrogen. We'll talk about the naming later. This is an incredibly important bond. This is what holds your proteins together. It's incredibly strong, which is why you can, when you cook your turkey, on Thanksgiving morning, it's you can keep it in the oven at 300 degrees, whatever it is, for 6 hours or 5 hours, however you want to cook it. Or if you smoke a brisket for 6 hours, or you cook up your corned beef, stuff like that. So that's what's holding those proteins together. Now the protein will unfold, but the bonds themselves won't break. It's because this thing is incredibly resistant to cleavage, to hydrolysis. And so if you really wanted to break that down, what you'd have to do is you'd have to boil this in acid for an overnight, and then those would break down. But otherwise, just boiling it in water or putting it in an oven isn't going to do anything. So the other one that has nitriles is the other one that has nitrogen is what's called nitriles. But this is very specific. It's a C triple bond N. And there is a set of lone pairs on that nitrogen, stuff like that, and so they all have CN. So you sometimes just see it as CN. Sometimes you have it written out like this. Sometimes it's written out like in the skeletal structure like this. These are all nitrile groups. You just have to know that it's a triple bond. So it's very, very specific. So with that, so acetonitrile, this is again a commonly used solvent. It's great, it's typically used as a polar solvent in HPLC separations. This chart from the table 2.3, what you guys need to know is you need to know the name and the sort of be able to pick out what that functional group is. You need to be able to see that in a structure, circle it, and name it. So like that. So we'll go over a couple of examples here. So like that. So just these here. Now I think the example has a couple that may have a couple that aren't on here, but yours will. So like that, because I wanted to get a couple that were. So like that. So a couple of examples, real world examples. So what I really want to be able to do is come in here and have you, if you get a prescription, lots of times in the packaging they'll have a they'll actually have the skeletal structure written out in there, stuff like that. So the first one here is atorvastatin. It's Lipitor. So like that, so it's used for cholesterol lowering. Actually, when I was at Pfizer, I actually worked on this, manufacturing this drug. So is a massively best-selling drug, massive blockbuster. So most blockbusters are considered, if you have $1 billion a year, at its height, atorvastatin was selling $14 billion a year. So it was actually doing a blockbuster a month, stuff like that. So every month in sales was over $1 billion. So what you're going to want to do is with this is come in here. Now when I do it, I exclude alkanes, cycloalkenes, and benzenes. So this is a benzene here, so you don't actually have to worry about it. So here, here, and here, those are benzenes. Don't have to worry about it. Stuff like that. But for here, you just sort of start on one side and go to the other. So here, this is nitrogen, but it has a C double bond O next to it. So this, what you do is circle it and say this is an amide. Okay. Come over here, a nitrogen. It doesn't have a C double bond O next to it, so this is an amine. Okay, these are just regular double bonds. It's actually part of an arene, but for our purposes, this is going to be an alkene here and here. Okay, going across here, these two are alcohols because they don't have C double bond O's next to them. Okay, there is this C double bond O, but there is a CH2 next to between it, so that makes all the difference. This OH has this C double bond O directly next to it. So this is a carboxylic acid. Okay. Okay. The next one is singular. It's used for allergies. So like that. So this has the this wedge because this sulfur atom's coming out at you. So with that, so we talked about that in the last chapter. Now one of the problems is this is, again, when I make up your molecule, this whole thing is actually part of a benzene. It's an extended thing, and this is a type of amine. Okay, so with that, and then here, so if you started benzene with another E, and here's another one, right? But here, that's a halide. You can also say chloride. That'd be fine. So if you come in here, this isn't on your chart. So by that, this wasn't come up, but this is called a sulfide. Okay, it's the sulfur version of an ether. So by that, so you come in here. This is actually a ring. Okay. So like that. So this is, even as 3-membered, it's a cyclohexane or cyclopropane, cyclopropyl group. So like that. So you don't have to worry about that one. Here another OH with a C double bond O next to it. So this is a carboxylic acid. Okay. Oh, I forgot to put this in. There's an alkene down here. I forgot to write before. So like that. So this is a benzene. So I don't have to worry about that. So with that, so usually you just end up going like around here and then come around here. This is a benzene, so you don't worry about that. This is an OH, but there's no C double bond O next to it, so this is an alcohol. So what you're going to do is it's going to look like this. Yeah, don't worry about those alkenes. That's kind of a quirky little thing. So this is the type of stuff you're going to see on the test. Okay. Okay, so for melting points, boiling points, stuff like that. So what we think about is the intermolecular forces. So how do the atoms interact with each other, or the molecules interact with each other? And generally, the stronger those interactions, the higher the melting and boiling point, something like that. So there's a lot of interaction between water molecules, and that's why it takes your water so long to, when you're cooking your mac and cheese, that's why it takes so long for that water to boil, something like that, to get the pasta ready. But whenever you're dealing with phase changes in any chemistry class, just think of water. That's one of the few substances you deal with every day that you interact with in the solid, liquid, and gaseous state. Stuff like that, and then and the terms. So melting is going from solid to liquid. Going from liquid to solid, that's freezing, right? So liquid to gaseous phase, that's boiling. So with that, and going from gas to liquid, that's condensation, right? When you have your drink out, stuff like that on a hot day, hot muggy day, right? You get the condensation on the outside. That's what it's called. So just think of it, whenever you're thinking about phase changes, just think about what water does, and you got your answer. Okay, so you have these ionic interactions, right? So one of the interactions is ionic, right? So for salt, think the different ion is these are some of the strongest interactions out there. You've got a positive charge, negative charge. It's given an electron over there. So by that, this is going to be, and that's why salt crystals have such a high melting point, right? It's like 700 degrees or something like that, some insanely high number. Now you can also have what are called dipole-dipole interactions, and that's where if you have these polar covalent bonds, right? So by that, right here, so the negative on this side is going to be attracted to that positive there, and then this negative is going to be attracted to another one, and so they kind of line up, right? Positive, negative, positive, negative, positive, negative, and it's fairly weak. Stuff like that, but it's still important, stuff like that. So, and really, the larger this difference is, the larger the dipole moment of this, the stronger the dipole interactions. So that makes sense. Think of it as the larger positive and negative charges, the stronger they're going to be attracted to each other. Okay, you can also get this hydrogen bonding and stuff like that. And so this is again this sort of subset of these dipole interactions, but it's dealing specifically with hydrogen. And so you have these donors. Okay, so you're talking about NH bonds, OH bonds, FH bonds, anything where you have a polar covalent bond with a hydrogen. Okay, so you're going to have this. This is going to be a negative side. This is going to be the positive side. So with that, now carbon-hydrogen bonds, those aren't going to be part of this. Okay, so this has, these are donors. Okay, and pretty much anything with a set of lone pairs, so nitrogen, right, oxygen usually has two, right, fluorine, right, has these right here. This interaction here, okay, this is an acceptor, right, because it accepts the hydrogen. Oops. So with that, so acceptor, if I could spell, right here. So with that, right, because this is going to be a partial negative, right? So these are going to get, this positive is going to get attracted to that negative, or vice versa, however you say it, right? And that's actually particularly strong. It's not as strong as the ionic bond, but it's stronger than most normal dipole-dipole interactions, and stuff like that. And so it sort of falls in between those, stuff like that. But it's incredibly important in hydrogen, or in biology. It's what holds the strands of DNA together, stuff like that. And so between A and T, you're going to have two interactions. In G and C, you're going to have three hydrogen bonding interactions. And you think about you've got 1 million base pairs, stuff like that, and each one, assuming it's equal, AT and GC content, you're talking about 2.5 million hydrogen bonds, stuff like that. And so even though they're fairly weak, if you have 2.5 million of them, right, it's going to be pretty strong to hold those things together. It also holds together the secondary structure of proteins, right? So you have a beta-pleated sheet. You're going to have the hydrogen bond donors from one side interacting with the hydrogen bond acceptors on the other. On the other half of the chain, this part of the chain interacting with that part of the chain, stuff like that. And so that can do this. So this is a pleated sheet. An alpha helix is also going to do that. You're going to have that for when you have, this can be involved in quaternary structure, where you have two chains two specific chains interacting with each other. The hydrogen bonding is going to be important there, along with some other things, stuff like that. So biology uses this quite a bit. stuff like that. And so the more hydrogen bonding donors and acceptors you have, the higher the melting and boiling point. Okay, and so here in this molecule, right, this one's that one's an acceptor because it's got a lone pair. Another acceptor's got a lone pair. This one also has 2 acceptors because each one of these nitrogens has a lone pair. But this one has 1, 2, 3, 4 donors. This one only has 2. And so this one is going to be the higher boiling because it's got more potential interactions with each other. So like that. So, okay. So induced dipole-dipole interactions. So these are typically called either dispersion forces or London dispersion forces. So this is Fritz London. He was a Duke chemistry professor, my alma mater. Stuff like that. So he would have won a Nobel Prize, but he was killed in an automobile accident in 1954. Stuff like that. And you can't get the Nobel Prize posthumously. Anyways, so what he noticed is that if you look at just straight hydrocarbons, sort of alkanes, there's no real you would think that there'd be no real interactions. There's no dipole-dipole. It's all covalent bonds. There's no dipole moment to speak of. There's there's no hydrogen bonding. There's no ionic bonding. And so what he noticed is that every once in a while you will get the part of the electrons will just as they're whizzing around the floating around the the naturalists. Every once in a while you'll get they'll accumulate on one side just spontaneously. Well, that means that this side of the molecule, it's starting to get a negative charge. Well, it's going to repulse the electrons over here, and so you're going to push those up there, and so now these have an instantaneous dipole where there shouldn't be, but this happens and stuff like that, and so this one's going to induce this one, and this one's going to induce this one, and on and on and on, and then it goes away. Stuff like that, and then it happens again, and it happens frequently enough that you can get a bit of an interaction with each other, and this is what allows alkanes to actually be solids and liquids. Otherwise, they'd just all be gases, right? They'd all be all be like helium, stuff like that. So this is what you've got. So that how easily this cloud is distorted is makes it more interactions, right? A higher likelihood of these London dispersion forces, and so we call it the more polarizable it is, the higher the melting and boiling point. Well, how do you know about the polarizability? What you're looking for is actually how long, sort of how strung out it is. Okay, really compact carbons. So these each have 7 carbons in them. This is fairly compact, like that, and so that's going to have a fewer London dispersion force interactions, and so it's going to have a lower melting point. This one is strung out a little bit more. The carbons are in a long chain, so by that, so this is going to have a higher boiling point here. So by that, so the more strung out those carbons are, the higher the boiling point. Okay, so the other terms to know, and we'll talk about this more when we talk about solubility next, is this term called hydrophilic and hydrophobic, right? So with that, so you can't get away from your Greek and Latin roots when you get into science. So with that, hope you studied those in high school. So with that, and so hydrophilic means water loving, right? So with that, it dissolves in water. So with that, and so those typically are small alcohols, ketones, carboxylic acids, very small amounts of carbon, in them, stuff like that, either small amounts of carbons or they have a lot of groups associated with them. Hydrophobic, they're water-fearing, which means that they don't like water, and so these are long-chain alkanes, stuff like that. So lots of carbons associated with them. You don't get good interactions. So oils, stuff like that. So we always talk with solubility, we think about like dissolves like, but they never tell you why. And what it turns out that what you're doing is you're saying, are you disrupting the interactions? So by that, compared to the pure solvent, once you mix the components together, are you disrupting any of these forces? And so hydrogen bonding is more stronger than dispersion forces. If you're disrupting these hydrogen bondings, you're really not going to get very soluble, because what you really want to do is not disrupt a stronger force. Okay, so you have hexane and pure water. So in the hexane, this is a hydrocarbon, just straight on to alkane. The only force you have is London dispersion forces. With water, you have hydrogen bonding. Right, so with that, if you mix it together, you're disrupting the hydrogen bonding. So that's why they don't mix. Okay, but if you have ethanol, that also has ethanol and water together, they both have hydrogen bonding. So when you mix it together, that hydrogen bonding now might go between different molecules, but that's fine. You say the hydrogen bonding still exists and it's still the driving force, and so you're fine. And so the more likely you are to disrupt the hydrogen bonding or dipole-dipole interactions, the more soluble you are in there. So okay, so which is the most soluble in water? So you're looking for hydrogen bonds. So in this one here, this is pentane. That's all that has is dispersion forces. This ether here, so this is what, methyl propyl ether. This one here, this is gonna have hydrogen bond acceptors, but not hydrogen bond donors. So by that, so this might be slightly soluble in water. So by that, and so, but it's a lot of dipole-dipole interactions. So here you've got an alcohol here, so you have a hydrogen bond donor and acceptor, and so you're going to have this is going to be the most soluble in water because you're not disrupting the hydrogen bonding hardly at all. Okay, so solubility of ionic compounds, stuff like that. So you're going to want to put these into polar molecules, stuff like that. So the increasing dipole of solvents more likely to dissolve the salt. Now, there's some caveats to that. So with that, because what you're going to do is you're going to have the positive side of that solvent go to the negative side, and the negative side go to the positive. So with that, and then what happens is you have more than just one, right? It's what's called solvated. You're going to have them all the way around because there's usually a lot more solvent than there is molecule that you're dissolving, the solute. Stuff like that. So for hydrocarbon length and solubility, right? You got hydrophobic, hydrophilic. Stuff like that. So increasing the number of carbons decreases the water solubility. So if you have one alcohol group, up to about 3, soluble, no problem. But if you have 4, you're starting to reduce the solubility. 5, 6, 7. Once you're to 7, you have almost no solubility in water. And what's happening is this long carbon chain is just the dispersion forces are starting to get much more significant. And it's able to swamp out the OH, the hydrogen bonding here. And it turns out that the carbons to hydrophilic functional groups, if that balance is more than 3 to 1, you're gonna drop that solubility. And so here you've got 1, 2, 3 carbons and 1 OH group, so it's 3 to 1. So this should be soluble, no problem. And actually we see that here, propanol, right? Soluble, no problem. Here we've got 1, 2, 3, 4, 5, 6. So it's 6 to 1, so no way it can be soluble, and you have that here. And so hexanol here, very, very low solubility. For here, right, you have 1, 2, 3, 4, 5, which might be a problem, but we have 2 polar groups here, stuff like that. And so really it's 5 to 2 or 2.5 to 1, which is well below the which is fine for solubility, stuff like that. And so these 2 are going to be soluble in water. So it's this magical 3 to 1 ratio. Okay, so polar protic, polar aprotic solvent, stuff like that. And so if you have a protic solvent, you have hydrogen bond donors, stuff like that. So basically, you can think of it as you have a hydrogen, at least one hydrogen that's not bonded to carbon, stuff like that. And so because if you have any if all your carbons are bonded to, if all your hydrogens are bonded to carbon, then it's an aprotic solvent. So water, right, it has both of its hydrogens bonded to oxygen. Here, it does have CH bonds here, but it has 1 OH bond. That's all you need. So with that, so here for acetic acid, so with that you have an OH bond here. Here, DMSO, all of these hydrogens are on these 2 methyl groups. They're CH bonds. Again, CH bonds with acetone. Here, CH, and even here, right? This is a CH bond, right? So all of these are aprotic solvents, right? So when I talk about protic, really what it's shorthand for hydrogen. So with that, so an H, right? So if you have, H atom here, right? So you have one, you have a proton in the nucleus, and you have 1 electron. Okay, if you strip this away, so the electron goes away, the electron goes away, all you're left with is just that proton in the nucleus. Okay, so plus charge overall, right, because you don't have anything to balance it out. This literally, an H plus molecule is literally just a proton sitting around and stuff like that. And so when we think of an H plus, that's technically a proton, but it's sort of gotten sloppy in the fact that now any hydrogen is considered a proton. So proton meaning that it has a non-CH bond, so that an H not to a to a carbon. Here, all the hydrogens are on CH bonds. So that's where the protein. So aprotic solvents, protic solvents can generally are much better about dissolving ions, stuff like that. So, but so for that, because they have the hydrogen bonding, they have other interactions. But for aprotic, you're just talking about dipole-dipole interactions, and so not so bad getting the for like DMSO, the oxygen of the DMSO can come in here and get really close to the cation here, this is sodium. But the problem is the negative, that's the negative charge on the oxygen. The positive charge on the sulfur, it has these methyl groups in the way, and so it has a hard time getting close to the say the chloride molecule. And so it's a little bit tougher for this because of steric repulsion in there. You're trying to jam some methyl groups in there, it just doesn't work real well. Okay, so for soaps and detergents, how these work is the fact that you have a highly large ionic head group, so for that, or at least a very, very polar head group at the front, or here, and then you have a long hydrophobic tail. Okay, and so how does this work? So sometimes you'll see sodium dodecyl sulfate. That's this molecule here. It's also sometimes called sodium lauryl sulfate. So the way that they do is this part of the molecule. If you dump this in water, this part is going to hate it because it wants to be in with other hydrocarbons, right? So it's going to self-assemble. This part here loves being next to water, right? Because it's charged, it's ionic, it does all the things I like to do. And so what happens is it forms these capsules. It self-assembles into these capsules where you have these greasy core and then these ionic sort of shell, stuff like that. So you think of an M&M, right? So the chocolate in the middle, that's the hydrophobic part, and then the candy shell, that's where that's the part sticking out to the water, and stuff like that. And so it just self-assembles like that. So what happens, the way this works, is the fact that if you have a stain on your clothes, when you put it into the washing machine, right? So anything that's water soluble, it's just going to get dissolved in the water. The problem is the greasy parts. What's going to happen is this is what's called a micelle. So with that, what's going to happen is this is going to bump up next to one of, as the wash machine is going, this is going to bump up against next to that greasy stain. That grease is going to say, I don't like being in this water, but there's this nice greasy patch inside this capsule. So I'm going to hop inside of here. Well, this is floating around in the water. Well, you've got it pulled it out again. It's a fabric. When you drain the soap away, right, it's going to take everything with it, right? So that's why it's important to rinse things off after you get soap on them, because it carries away the grease, stuff like that. And so that's what's going on here with that. So you're just using this solubility differences to clean. Okay, so last part is going to be IR spectroscopy, stuff like that. And so for this one, we can for a lot of the spectroscopy, what's happening is you're shining different wavelengths of light in there into the molecule, and the way that the molecule interacts with that light is called spectroscopy. Lots of times it'll absorb that energy or get excited or whatever, stuff like that. And so in this particular case, we're going to be shining infrared light, which is down here. It's fairly low, it's in the little laser pointers with that. So it's in this region down here. So with that, what happens is this will excite the natural wiggling of those bonds. So with that, and so what happens is you get these stretches and wiggles and asymmetric stretches and in-plane bending and all that sort of stuff. But these have very specific frequencies, and if you hit it with the right frequency of light, you can excite that. You hit it, the resonance of it, and so that, and so the molecule absorbs that, and so that. So you can think about if you're trying to speed up a merry-go-round or trying to push a swing, you can't just hit randomly; it doesn't work, right? So with that, but if you hit it at a very specific frequency, you can get that to go faster and faster. That same thing's happening here, and so what happens is you shine a bunch of different wavelengths of light, and so you usually give this in wave numbers, and all it is it's 1 over the wavelength. Stuff like that, and so bigger numbers are smaller wavelengths, which means more energy. It's kind of weird, but it's basically what they're trying to do is they're trying to get out of from little numbers, stuff like that. So they give this wave numbers, and so what's happening is, so this is percent transmittance. So we know how much light we put in of each wavelength. and stuff like that. So all of it's going through, so nothing's happened. So this is one of the weird ones where in spectroscopy where way up here means that nothing's happening. And then you get to this wavelength of light, and it absorbs a bit. And then when it gets to this wavelength of light, you hit a lot of absorption, because there's a lot of these bonds that are wiggling around. And then at these frequencies, nothing. And then say at 1700 wave numbers, it also absorbs, and then there's a bunch of absorbing here, stuff like that. And so if we look to see where these things absorb, you'll be able to, they're fingerprint regions, stuff like that. And so for this one, so this C double bond O, this carbonyl structure is very characteristic of absorbing right around 1700 wave numbers, stuff like that. And so this one, it shifts a little bit depending on the type, but for the most part, it's going to be 1700. If we see a peak here, we know we have a C double bond O in our molecule. Okay, there is this IR spectra chart. You do not need to memorize it for my tests. Now, you will for the MCAT, for the ACS final, you'll need to know those. But, and we'll get to this in a second, there's a trick to know this, know these. Okay, and so if you're looking at these molecules here, stuff like that, and so here you go on this chart, stuff like that, and so this alkene here, this bond, that's going to absorb, so the alkenes, it's right here, it's going to absorb somewhere between 1620 and 1680 wave numbers, so it's going to be somewhere around in there. This C double bond O, it's part of an ester group, stuff like that, so you come in here, so that's going to absorb somewhere between 1730 and 1750. This CO bond here, it's going to absorb between 1050 and 1150 wave numbers, and this regular alkane CH, that's going to be 2800 to 3000. Stuff like that. I mean, these other things are going to have absorptions, but these are the ones I'm highlighting. Stuff like that. So, okay. Now, again, you don't have to memorize this chart. What you can do is you can kind of look at this here, stuff like that. And so this part here, from 2500 on up, these are things bonded to hydrogen. So CH bonds, OH bonds, NH bonds, anything bonded to hydrogen, that's in this region here. In this 2000 to 2500 region, these are anything that has a triple bond. So C triple bond N, C triple bond C, things like that. Stuff like that. So here, from 1500 to 2000, that's in the double bond region. So 1700, right? That's for C double bond O. That's right in here. Right? So, so the other ones are carbon-carbon double bonds. Those also come in here in these regions. Now they're shifted a little bit. So they're shifted a little bit, right? So so alkenes are 1620. So they're going to be a little bit over here. So like sort of in here, but they are still going to be in this region. Here, these are all just regular, single bond structures, so carbon-carbon single bond. Now, things that aren't the CHs, right, that's over here. But carbon-carbon double bonds, CO bonds, CN bonds, CS bonds, whatever, that's going to be here. And then these bending modes, these are over here in this last one. So 1000 to 1500, single bonds. 15 to 2000, double bonds. 2000 to 2500, triple bonds. 2500 on up, things bonded to hydrogen. So if you know that, you can get pretty far. Okay. So for that, so again, the characters. But if you want to look at some specific ones, you C double bond O. So for that, so depending on which they are, they're going to be shifted slightly, but they're all going to be right around 1700. Okay. Now you do have to be careful, because if this is what's called conjugated, so if it's just a regular C double bond O, it's going to be 1700. But if it goes double, single, double, okay, it's going to actually shift that down about 30 or 40 wave numbers. It just changes the frequency of this signal. So if you see something that's slightly off, that's why. It could be this C double bond O. Okay. Another peak is the OH and NH peak. So they're right around, because they're in that region above 2500, they're actually right around 3000 to 3500. Stuff like that. But the characteristics, if you see a spectrum, you'll know it. Stuff like that, because OH peaks have a really big hump. Stuff like that. So if you see a big hump like this, there's an OH group in there. Stuff like that. As opposed to an NH group, it's a much, much, much smaller hump. Stuff like that. So it's a more normal peak. Stuff like that. And so if you see that, I've got an OH in there. Okay. There are some aromatic substitutions. For my test, we're not going to worry about this because we haven't talked about ortho, meta, and para substitution. When we deal with naming, we'll come back to that. But these have very specific. So monosubstituted has 2 peaks, 2 very specific peaks. Ortho substitution has 1. the meta substitution has 2 different peaks compared to the mono substituted. That para substitute has 1. So by that, so this is in that region below 1,000. That's usually where these pop up. Okay, so to do structural elucidation, what I'll do is I'll have this spectrum and I'll say, hey, which one of these molecules corresponds to this? Okay, so we look at this one, 2900 or 2950. You come over here and you look and you say, okay, so what could it be? Well, it could be a carboxylic acid OH. Well, I don't have that in here or here, right? So that, but when I have here, the 2950, now it could be the alkane. So but that's alkane. So with that, so the alkene, it can't be that. Alkyne, nope. 20, it's outside of here. So with that, so it's just the regular alkane, the CH peak, which both of them are going to have. Now the 2150, you come over here. Ooh, it could be a nitrile. Well, I don't have a nitrile. I have an alkyne. So like that. So it's going to be one of these two, right? Well, it can't be the nitrile. So if it is, so because it's a we just don't have that group, right? It's an alkyne, so they both have that. Now the question is, which one of these two? Because they both have the alkyne, and they both have they both have this alkyne. They both have the alkane CH. So which one is it? Well, it turns out it's this one. Okay, because in order for these two to represent this molecule, we'd have to have a third peak. And specifically, notice how this carbon here only has 3 bonds. There's a CH peak here. And so we would have an alkyne CH bond or peak that would also have to show up. So with that, and so for this one here, you're going to have that one, and that 3300 peak. So by that, so you have to think about what's there and what's not there. What's not there can be just as important as what is. With that, so if you're looking at structural elucidation, right? So with that, so what you can do is you can take, you can use this to monitor reactions. Sometimes this comes up in the lab. So you look at what kind of functional groups you have in here. Well, you're going to have the alkane CC bonds. You're going to have alkane CC or CH bonds. So they're both going to have those. Okay. This one is also going to have an OH peak right here and a CO peak, which is right there. This one over here, this one is going to have those alkane peaks, but it's also going to have a carbon-carbon double bond with that. So, but it's also going to have this alkene CH. So this CH bond coming off of the alkene here. So with that, and so, but it's also going to have the OH, right? Because we're making water. So the OH probably isn't going to change much, but what's going to happen is, as this reaction goes along, if you're taking readings, this CO bond is going to go away, right? Because we're losing the concentration of this, and what's going to be growing in is this this peak here and that peak there. So with that, as we start to make more of this compound, so that's how you do this. See what's different between the two. Okay, good luck.